In this section, we're going to talk about volumes of solids. And this is really an interesting thing that is related to integration. It's really fascinating how we can find the volumes now of different items, either revolving around an axis or a line or just different shapes in general. It's just really cool. So what we're going to look at is volumes of solids. Almost any solid you can think of, as long as there's some sort of function that goes with it. And the volume of a solid of a known integrable cross-section of area, okay, we'll call that AX. So in other words, we need to know how to find the area of some shape. From x equals a to b is the integral of this function a from a to b. It looks like this, okay? So if we integrate the area, okay, the area times the change in height, all right, then when you have area times height, you have volume. Okay, and so the first problem we're going to look at deals with a pyramid shape, and so it's kind of hard to draw 3D-ish, but basically what we're looking at is some sort of pyramid guy that creates a square and it comes back to the origin, something like this. Okay, and what we're wanting to do is we're wanting to find the volume of this whole shape in here. We want to find the volume of that whole shape. But how are we going to do it? We're going to find the area of the square that's dotted. We're going to find the area of that guy, and then we're going to look at an infinite number of little slices along the x-axis coming back. So we're going to take a little slice, 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 and we're going to do this. And when we integrate that with all those little heights and add them all up, we get the volume. Okay, so area equation times dx equals volume, especially when you integrate it. So some tips for finding volumes by doing this little slicing method is to find a formula for the area. Okay, sketch out what your graph might look like. Find the limits, so where are you starting and stopping, and then integrate it. And if you're one of my students, you have total permission now to use the calculator to help you. We did our test previously with integration. If you're not one of my students, then you will need to go ahead and show all your different steps. So let's look at one. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross-section of the pyramid parallel to the base is a square. Find the volume of the pyramid. Now, this is going to be a little difficult to draw, and I'll try and draw it as best I can, but I am not a super great graphic 3D artist. So this would be the x-axis kind of coming at us. Here's the y-axis going straight up. And basically what we're looking at here is a situation where we've got this pyramid shape, and it told us it had square pieces. All right, so let me clean this up just a little bit here. Remember, that's x, and then so all these different corners come back to the origin. Okay. And what we're wanting to do is we're wanting to find the area of this part right here. This guy right here. What's the area of this square? Okay. And if we think about the area of this square, we are x units wide. Okay. We're x units here. We're x units here, we're x units here, we're x units here. And we're also, to that point, x units. Okay? So we've got these straight lines all coming off all over the place. And we're told that our pyramid is 3 meters high. So if this is 0, this right here where our last line is 3. So we know we're going to integrate from 0 to 3, okay? And we know that we've got all these different little squares in here that we're trying to find the area of. Well, how do you find the area of a square? You do a side times a side, or x squared. And then we also need to multiply by the width of each square, so that would be dx. Okay? And how do I know that each one of these is x units in length? Because I know that I've got congruent triangular sides and a square base that's 3 meters on each side. So if my base comes down here to 3, this guy's 3, this guy's 3, this guy's 3, this guy's 3. So everything is all in relation for this particular setup. So integrate this guy. We're going to integrate him. He's going to be x cubed over 3, evaluated from 0 to 3, which will give us stop minus start, 3 squared, 3 cubed divided by 3, minus 0 cubed divided by 3. And when you punch that in, you're going to wind up with 27 over 3 minus 0, or 9, and then 9 what? 9 meters cubed. Now, this first guy looks really complicated. We weren't necessarily given a specific equation to work with, but use your brain here. I mean, we've got a distance from 0, and everything's in relation. So that's how we know that we have x's all over the place. If we just pick some random spot, we are x units from the origin, and the sides are x units long. Okay? If we're given a function, that makes our job just a little bit easier. All right? And we'll see several examples of this coming up. But there you go. Here's my area equation. Here's my height. I got to have that. I know what I integrate from, what I integrate to.